It's an honor to be here. Thank you to the organizers. And thank you to the audience for getting up early and braving the elements and coming here. And unfortunately, I never met Nambu, but given his contributions to spontaneous symmetry breaking and to the introduction of Nonabelian gauge theory into mainstream particle physics, I thought an appropriate topic for today's talk would be my work on magnetic monopoles. So the title of the talk, Monopolia, is meant to evoke explorations in the land of magnetic monopoles. And it's also a reference to an idea I had as a graduate student, where I decided it was time to update Albrecht Dürer's masterpiece, Melancholia, to reflect modern developments in speculative philosophy. And I had in mind something like this. Now, that was back in the day before Bill Gates had made the kind of vandalism you're witness to here both possible and even easy. And indeed, at the time, I tried to implement this. I was never very satisfied with the result. And so imagine my astonishment when a few years later, I opened Robert Dijkgraaf's PhD thesis, and I saw that. So Robbert had exactly the same idea, and unlike me, Robbert implemented it rather brilliantly. And I commend this slide to your attention. The talk's on my homepage. You know, instead of the Kabbalistic signs on the wall, we have the elementary particles of the Standard Model. Instead of the, I also changed the Kabbalistic signs. Instead of the sleeping bull, we have Schrödinger's cat, so on. Okay, so lots of goodies to dig out there. Now, this project, more specifically, is a project I've been undertaking for a few years. It's done now with Andy Royston and Dieter van den Bleeken. And indeed, some of you will remember at Seoul, Korea, at Strings 2013, there was one of the headlines of that edition of the BPS Times was this project here, which is now completed. And later on in the talk, this headline is actually also going to play an important role. So here's Andy and Dieter, and these are the 4 papers we wrote. Andy, of course, is well known here. He's Jeff Harvey's student. And the motivation for our project has been some nice progress in understanding BPS states and 4-dimensional n=2 supersymmetric field theories. And I'll focus on the no exotics theorem, mostly, a little bit about wall-crossing formula, and maybe I can squeeze in a little bit about exact results for line defects at the end. And very much in the spirit of some papers that were written in the mid-90s by Sav Sethi and Jeff Harvey, we want to take this new physical insights and say, what can we learn about mathematics? More specifically, what can we learn about the differential geometry of monopole moduli spaces using these recent physical results? So here's the outline of the talk. I'm going to spend a fair amount of time reviewing things and only really get to the new stuff towards section 7 and 8. So let's begin. Of course, it's the morning after the banquet with daylight savings time into the bargain, so I thought I better start slow with a little Lie algebra review. So let G be a compact, simple Lie group with Lie algebra little g. Then we say an element in the Lie algebra is regular if the centralizer of X has minimal dimension, in which case it serves as a Cartan subalgebra. You can exponentiate that Cartan subalgebra to get a Cartan subgroup, and then you can define 2 lattices. One is the lattice of homomorphisms from T into U1, called the character lattice, and the dual lattice, the homomorphisms of U1 into T, is called the co-character lattice, And you could think of that as the Lie algebra elements that exponentiate to 1. And again, oriented, you see the character lattice sits between the root lattice and the weight lattice in the dual of the Cartan, and the co-character lattice sits between the co-root lattice and the magnetic weight lattice inside the Cartan. And of course, the root lattice is the dual of the magnetic weight lattice. I'll use that later in the talk. And the weight lattice is the dual of the co-root lattice. Moreover, a regular element determines a set of simple roots. So I'll denote those as alpha I, and simple co-roots, h sub alpha I, or hi. And then the root lattice is just the integral span of the roots, and the co-root lattice is the integral span of the co-roots. So, for example, here is a Cartan subalgebra of SU3 with a set of roots. And if I choose that regular element, then it singles out that set of simple roots. But if I choose that regular element, it singles out that set of simple roots. Okay, enough Lie algebra review. So now let's talk a little bit about magnetic monopoles. So we'll start with the Yang-Mills-Higgs system for a compact simple group G. So the fields are a gauge field or a connection A and a Higgs field X with a very simple Lagrangian. And we're interested in time-independent solutions, the Bogomolny equations on R3, subject to the boundary condition that the field strength out at infinity is proportional to the volume form on the two-sphere times some element of the Lie algebra, gamma m, and the Higgs field goes to the Higgs vacuum expectation value, x infinity, and then the rest of the expansion is determined by the Bogomolny equations. Now, we will assume that the Higgs VEV is a regular element, so as I just explained, that implies we get a Cartan, simple roots, and simple co-roots. And indeed, the magnetic charge, gamma m, is quantized to be in the co-root lattice. So it can be expanded in terms of the simple co-roots, and these integers are the magnetic charges. So now we can look at the moduli space of the solutions of these equations, modulo gauge transformations, that go to 1 at infinity. So if M is non-empty, then a classic calculation shows that the dimension of the moduli space is 4 times the sum of the magnetic charges. When is M non-empty? It's known to be non-empty if and only if all the magnetic charges are non-negative and at least one of them is positive. Known result. Okay, in that case, M is a smooth manifold. It has a hyperkähler metric. That metric has a group of isometries with Lie algebra R3 for translations of the monopole, rotations around some origin, and global gauge transformations. Now, the global gauge transformations are going to be very important for what I talk about later in the talk, so let's make sure we're on the same page on that one. This is a baby version of what Andy Strominger was talking about last night. So if H is a generic element of the Cartan, then there's a corresponding killing vector field on the monopole moduli space, G of H. And to define it, you can look at the Bogomolny equations as the self-dual equations, where they're X4, where you look at X4 independent solutions and you consider the Higgs field as a fourth component of a gauge field. And in that language, the directional derivative along G of H at this A hat is just a gauge transformation where the gauge parameter epsilon doesn't go to 0 at infinity, but it goes to this element H we started with. And to make this unique, we have gauge conditions, and so epsilon should be harmonic. Now epsilon is unique, so that is the action of the global transformations. Now, another thing we need to remember about magnetic monopole moduli space is the strongly centered moduli space. So if you go to the universal cover, then the moduli space factors metrically as a product of R4 and M naught. The R3 comes from translations. The R is the orbits of the global gauge transformations in the direction of the Higgs VEV. And the M naught is the strongly centered moduli space by definition. The true moduli space is then the quotient by the deck group, and the deck group is isomorphic to the integers. That will be important later. Okay, now one of the themes of this talk is that higher rank is different. So many of you in the audience have written papers on this, and often this formula appears in your papers, but this really only applies to SU2. There's no finite index quotient that acts trivially on M0 at higher rank. Okay, so now let's talk about singular monopoles. So we again are looking at solutions of the Bogomolny equations with the same kind of boundary conditions at infinity, and we choose a point where our singular monopole sits, and we also say that as x goes to 0, that point's the origin, then f is again proportional to the volume of a 2-sphere with some element of the Lie algebra, the Hooft charge p, and the Higgs field has a simple pole proportional to p. Now this is used in the construction of Hooft line defects. Everybody else calls them line operators, but they're not operators on anything, so I call them line defects. And they were very important in an important paper of Kapustin's and played a crucial role in the paper of Kapustin and Witten on the geometric Langlands program. So what's an example of a singular monopole? Well, I hope most of you have gone through the Hooft-Polyakov Ansatz for SU2 gauge theory, where you take Higgs Vev in SU2 and you make it proportional to the Cartan with some function of the radius, and you take a Dirac monopole and you add Nonabelian degrees of freedom with some other function of the radius, and then the Bogomolny equations become this pair of ODEs, which you can solve, and if you solve them honestly, you'll find there's a constant of integration, this green C here. Now, Hooft and Polyakov and Prasad and Sommerfeld all took C equals 0, but C greater than 0 is the case of the singular monopole. So Hooft missed the Hooft line defect. You might wonder what's the physics of this C, and I'll give you a physical interpretation in a few slides. So now, again, we have a moduli space of these singular monopoles, solutions modulo gauge transformations. They now depend on P, gamma M, and the Higgs Vev. And we can ask some questions about this moduli space. When is it non-empty? If it's non-empty, what's the dimension? Supposing the Hooft charge, for example, is equal to the asymptotic magnetic charge. Well, people who ought to know better tell me, it's obvious, the P, that charge is all screened by the monopoles, and therefore the dimension is 0. So is the dimension 0 or not? I claim this requires a little bit of thought, and we thought about it. And if you assume the moduli space is non-empty, it's a pretty straightforward calculation to repeat the analysis of Callias and Weinberg. The dimension of the moduli space is proportional to the index of a Dirac operator on R3. The index of an operator on R3 is a little subtle, so you have to define it this way. But indeed, on a general 3 manifold, you find a formula which is an integral of a total derivative. You then can analyze that by Stokes' theorem. And in this case, on R3, you get 4 times the sum of what we call the relative magnetic charges. So what are the relative magnetic charges? Well, here's that formula again. The relative magnetic charges are the difference between the magnetic charge and P minus. So the gamma M comes from the boundary, the infrared boundary as R goes to infinity, and the minus P minus from R goes to 0. P minus is the Weil group image of P such that the inner product with all the roots is non-positive. And what determines those simple roots? Well, as I've stressed, that is determined by the Higgs Vev. So there's a nice little D-Brane interpretation of this formula. You can think of a D1, D3 system where you have vertical D3 branes and semi-infinite D1 branes ending on those. Those are giving you the singular monopoles. And in the Bion spike picture, the profile of the D3 branes is given by this Higgs Vev, and you read off right from this Higgs that this is indeed a case where gamma M is P. It's P1 minus P2. And so there are 2 cases. Notice that the chamber in which the Higgs Vev is living is the ordering of x1 versus x2. That's what determines the positive and negative roots. Anyway, if P1 is less than P2, then gamma M is P minus, the dimension is 0, and the D-branes look like that. On the other hand, if P1 is bigger than P2, then gamma m is minus P minus, so our formula says that the dimension is 4 times P1 minus P2. And indeed, in this case, you see the bion spikes intersect each other, and so our interpretation is that the branes rearrange themselves, and we get this finite number, of finite length smooth monopoles. So we think of P1 minus P2 smooth monopoles moving in the background of one singular monopole. So as an application of this picture, you can go back to the singular Hooft-Polyakov Ansatz. What does this see here? Well, again, from the Higgs vev, you can just read off that gamma m is P, so that means that the relative magnetic charge is 2. So that means that these solutions are exact solutions inside an 8-dimensional moduli space of solutions. And because of symmetries, you see what's going on is you've got 2 smooth monopoles sitting on top of a singular monopole, and with a little more thought, this constant C is just a relative electromagnetic phase. Yep.
The D-Brane picture, it looks like you could always do these singular monopoles as smooth monopoles in the case theory with one higher rank by adding.
Oh yeah. We worked that out in gruesome detail. Yeah. So we took finite monopoles and we pulled one D3 brane to infinity, and we took that picture and turned that into formulas and. Well, this, of course, is UN theory. And there's an interesting story about decoupling the U1. But, yeah, I wouldn't, this doesn't apply to, G2 or something like that. But yes, that all works very beautifully. And that's described, as I said, in gruesome detail in our paper. Okay, so that's one interpretation of C. You can also think of this as 2 D6 branes on an O6 minus plane, or in terms of 3-dimensional super Yang-Mills theory. It all depends on when you got your PhD. All right, so what are some properties of the moduli space? Well, mathematicians haven't looked at this enough. So we conjecture that the moduli space is non-empty if and only if all the relative magnetic charges are non-negative. And it's certainly hyperkähler, although it is singular because of something called monopole bubbling, pointed out by Kapustin and Witten. That, too, has a nice D-Brane picture, which I'll skip. And again, it has the isometries as before, but of course without translation, since the singular monopole at the origin breaks translation. So now that's monopoles. Now let's go on to n equals 2. Okay? So the first thing about n equals 2 super Yang-Mills is that we've got to add a second real adjoint scalar field y, and the vacuum expectation value of y has to commute with x. X is still going to be a regular element of the Lie algebra. And y and x are the real and imaginary parts of the vector multiplet scalar in the vector multiplet, but you're allowed to rotate by a phase zeta. So what's the meaning of a phase zeta? Well, you see, if you look at the BPS equations for this linear combination of supersymmetries, then if you define the real and imaginary parts to be y and x, respectively, then the BPS equations fall apart nicely into the old Bogomolny equations for x and then some secondary equations for y. Now, zeta also has a nice meaning in terms of BPS states. So you see, if you square this supersymmetry operator, you derive a BPS bound, that the energy is greater than or equal to minus the real part of zeta inverse of Z gamma. What's Z gamma? Z gamma is the n equals 2 central charge. So little gamma is the electromagnetic charge. You see, the Higgs vev has spontaneously broken the gauge theory down to the abelian subgroup. And we have electric and magnetic charges with respect to that. And capital gamma is the lattice of electric and magnetic charges. Now, by definition, BPS states are quantum states that saturate this Bogomolny bound. But the important thing for this talk that you need to understand is that there are 2 kinds of BPS states. There are framed BPS states. In that case, the phase zeta is part of the data that defines the 't Hooft-Wilson line defect. Okay? So you can't do any better. Zeta is part of the data. And we denote the space of framed BPS states for a line defect L with electromagnetic charge gamma at a point U in the Coulomb branch this way. Now, in the ordinary BPS states, which I'll call smooth or unframed or vanilla or ordinary BPS states, then we can choose any zeta we want. So we should choose the zeta which maximizes this bound here. So zeta should then be negative the phase of the central charge. And then we get a space of ordinary BPS states, which is what people usually talk about. So that depends on an electromagnetic charge and a point U on the Coulomb branch. Now, what we'd like to do is describe these spaces in the semiclassical regime. What's the semiclassical regime? Well, there are actually many and equivalent definitions, but for us, we'll take the usual Seiberg-Witten picture where we have AD as a function of A and the dynamical scale. So if all the inner products of A with the roots is greater than some suitable constant times the dynamical scale, these series converges. And in this region, the local system of electromagnetic charges has a natural duality frame. There's a natural way of saying that an electromagnetic charge gamma has an electric charge in the weight lattice and a magnetic charge in the magnetic weight lattice, except, of course, I've lied. Anybody know why I've lied? Is anybody awake? Well, what? I lied because this because I felt everybody was falling asleep. I'd better lie and see if you're awake. There's something wrong about what I just said, and if people don't recognize that, then you know. Is that the entire? Oh, definitely not. Oh, no. These BPS spaces can be the zero vector space. And indeed, for most charges, they are the zero vector space. And our goal is to understand when it's not the zero vector space. We sit at a point U in the Coulomb branch, we choose an electromagnetic charge gamma, and we ask, is this a zero vector space or not? Usually it's zero. No, the lie here is that we miss the Witten effect, right? You don't have a global decomposition of the electromagnetic charges into electric and magnetic because this semiclassical region is, after all, not simply connected. But you can trivialize that after choosing suitable cuts in the logs for AD. Now you take the dynamical scale to 0, and you can show there's no wall crossing. And so really, this space of BPS states stabilizes. That's the semiclassical space of BPS states. That's what we're aiming to describe. Now, in this regime, there's a well-known description of how you write these BPS states. At weak coupling, the BPS monopoles are heavy, so we can use the the moduli space approximation. And so the answer has to be something like this. The semiclassical states at U with phase zeta with electromagnetic charge gamma E plus gamma M should be described in terms of supersymmetric quantum mechanics on the framed or the smooth moduli space of monopoles, as the case may be for framed and ordinary BPS states. But of course, this way of putting it raises at least 3 questions. Question 1, what sort of superquantum mechanics? Question 2, how is U and zeta supposed to be related to the Higgs vev? And question 3, what does gamma E have to do with it anyway? So I will now answer those 3 questions. Yep. Yep. We are not. We are talking parallel throughout this talk about both ordinary and singular monopoles. So these funky overline and underlines is always indicating the framed case or the singular monopole case. That's right. That's right. Yeah, but there's still a strong coupling regime on the Coulomb branch. So maybe you're complaining about this bound here in the case of the singular monopoles. And the answer to that is, yes, the singular monopoles are infinitely heavy, but you see you cut out a little sphere around the singular monopole, you add suitable boundary conditions such that the theory is still supersymmetric, so that everything is consistent, and you take the epsilon goes to zero limit, and this is what remains. And again, that's, our paper is long for a reason. So, we did all those details in extreme care. But you raise a point that's important, which is framed BPS states are BPS states of the Hilbert space in the presence of this line defect. Okay, and there is there's a well-defined Hamiltonian with this bound on its energy, and we can talk about states saturating that. That's the framed BPS states. Nadi. Good question. Most of this talk is about the pure vector multiplet theory, and then I have 2 or 3 slides where I say what happens when we add hypermultiplets. Well, I'm trying to be careful about that. Look, okay. This talk is also about the pure 't Hooft line defects. There's a whole zoo of line defects, and I have another slide coming up later where I mentioned that with a student we're looking at generalizing the story to more general line defects. But I defined it when I wrote down the boundary conditions. I don't want to go all the way back. I defined it when I said what the boundary conditions are for the gauge fields. Yeah, that depends on the quantization of that P. So remember, the P, so we allow the P to be in the magnetic weight lattice. That's the minimal P. But if you want, you can just take P to be in the co-root lattice. That's the distinction. And we certainly allow P to be in the magnetic weight lattice. So where were we? So we had the 3 questions. What sort of quantum mechanics? How have you zeta related to X infinity? And how does gamma E have anything to do with it? And then people started asking me questions. Okay, but let's focus on these 3 questions. Okay, so what sort of quantum mechanics? That's where we left off. So what sort of quantum mechanics? Well, that was a subject which was intensively studied in the mid to late 90s by a number of people, some of them here. And the answer is that you get n equals 4 superquantum mechanics on the moduli space with a potential. So this is the usual kinetic term. This is the potential term. So remember those killing vector fields, G of H? So the potential is G of H squared, where the element H in this case, is made out of the Higgs vacuum expectation values in this way, with this curly Y sub infinity. Of course, a moduli space with a potential is a contradiction in terms. So really, we should be working in the weak potential approximation, but let's do that. Now, there are supersymmetric partners to the Z mu's. The chi mu's become gamma matrices, so the quantum states are spinors on monopole moduli space. One of the 4 supersymmetries is this operator here. The d mu is the ordinary Dirac covariant derivative, so this is just the Dirac operator. And then we're adding to the Dirac operator Clifford multiplication with this vector field, or more properly with the one-form dual to this vector field. And for simplicity, that's a big mouthful. So I'm going to just call this thing the Dirac operator, boldface D. But please remember when I talk about the Dirac operator, it depends on curly Y, okay? We're thinking of a family of Dirac operators parameterized by curly Y. That will be important later. All right, so question 2. How is U and zeta related to the Higgs valve? Indeed, we need to understand not only X infinity so we can construct the moduli space, but also Y infinity so we can construct the Dirac operator. And what we found, it's rather technical, but what we found is that this pair of formulas for going from a point U on the Coulomb branch in a phase zeta to Higgs valves works extremely well. It actually nicely encodes quantum corrections. And indeed, we argue that replacing in the potential G of Y classical by G of Y infinity actually allows you to go beyond the weak potential approximation. Now, in the remainder of this talk, I'm only going to be talking about vacuum expectation values, so to save writing, to save our eyes, I'm just going to call those x and y, but I'm always talking about vevs from now on. So now we're all set up to give the geometrical formulation of BPS states in the semiclassical regime. So let's start with an overview before we get into the technical details. Okay, so one of the four supersymmetries is this Dirac operator. And so the framed or the vanilla BPS states with magnetic charge gamma m is going to be a Dirac spinor satisfying the Dirac equation. Of course, it has to be suitably normalizable, so it has to be in the L2 kernel, and it has to be suitably equivariant, and there are a lot of devils in those details. Okay, so let's start talking about those details. Let's begin with the framed BPS states, and let's begin that discussion by talking about the electric charge. So the singular monopole moduli space has an action of global gauge transformations. And these killing vector fields G of H, they commute with the Dirac operator. So we can simultaneously diagonalize them. So on the kernel of the Dirac operator, we can diagonalize G of H, or better to think of it as the isometries given by exponentiating G of H. And what are the eigenvalues? The eigenvalues are just the electric charges which live in the dual of the carton. But you see, actually, it's not just the T that acts. It's the carton torus of the adjoint group that acts. The carton torus is T modulo the magnetic weight lattice. So what that means is that if H here is in the magnetic weight lattice, this phase factor must be 1. What that means is that gamma E is in the dual of the magnetic weight lattice, and early in the talk I reminded you that that's the root lattice. No surprise, electric charges should be in the root lattice. So now we should organize the L2 harmonic spinors by the carton torus representation. In mathematics, that's called an isotypical decomposition. So we take the L2 kernel, we sum over the root lattice of those elements of the kernel that transform in that way. So now we have a very clean answer to what is the space of semiclassical framed BPS states. The question is, L is in a 't Hooft line defect of charge P and phase zeta. What is the space of BPS states at the point U in the Coulomb branch we're using the semiclassical regime? So you take zeta, you take U, and you form X, and now using P here, and the magnetic component of gamma, you form this moduli space. Now you compute Y, you get your Dirac operator, and finally you use the electric charge part of this to take the isotypical component. That's the answer. Okay, end of story. Very clean answer. Now let's do the same thing for the vanilla BPS states. Well, the first subtlety is we have to start on the universal cover of moduli space, but the physical states must descend to the actual moduli space. Now, the story for the electric charge is exactly the same. T acts on M, T is little t mod MW. States of definite electric charge transform in a definite character, which is in the root lattice. All that's exactly the same. But then we have to separate out the center of mass degree of freedom for a reason I'll explain on the next slide. Now, what I mean by that is the universal cover is metrically R4 times M0, the strongly centered space. So we have to separate variables. We have to separate the Dirac operator and the spinors and solve the separate equations. The one subtlety I want to mention here is that in order to really do that separation of variables, you need a very surprising identity, at least surprising to me, which is that, see, if you take these killing vector fields, and you take one of them to be along the direction of the Higgs vev, remember that generates this real line here, and you compute that inner product in the hyperkähler metric, well, you can just calculate that by using the killing metric, infinitely easier, of the magnetic charge with H. And when I first saw this formula, I thought this cannot possibly be right, because x infinity is a general direction in the carton, and gamma m is a quantized magnetic charge on the lattice, but it seems to be right. Okay, now why do we have to separate out the center of mass? Well, you see, the point is, there are no L2 harmonic spinors on R4. Okay, so it would be wrong to put an L2 condition, and of course that's physically reasonable. We're describing particles. They're only plane wave normalizable. On the other hand, we certainly want the L2 kernel of the relative Dirac operator. We don't want plane waves in this relative space, which is also non-compact. And please contrast that with the hypothetical instanton particle of 5D super Yang-Mills, where we don't have that potential in the superquantum mechanics, and we have these vexing plane waves and the scale modulus, and nobody quite knows what to do with that, as far as I'm aware. But here we have that potential, so let's use it. So now we want the L2 kernel of D naught. So now it looks like it's a piece of cake. So we take the ordinary kernel, the L2 kernel of the relative space, we take the isotypical component, we use these formulas to translate from gauge theory, U and zeta, to these geometrical variables, and we take zeta in this case to be minus the phase of the n equals 2 central charge. Okay, so that looks very nice, except it's wrong. Why is it wrong? Well, there's a little tricky subtlety. So remember, I told you that spinors have to descend to M, and the deck group is generated by some isometry of the hypercalorimetric. And the subtlety is that by imposing electric charge quantization, you only impose an invariance under a proper subgroup of the deck group. You see, when we impose electric charge quantization, we're saying that these isometries act as one when lambda is in the magnetic weight lattice, and that's fine. But you see, these isometries are certain non-trivial powers of the generating isometry of the deck group. So what is this mu of lambda? Well, this is subtle, so let me put this in a slightly different way. So the Cartan torus acts on M. So choose any point you like in M, and you get the orbit of the Cartan torus in the moduli space. That means you have a map from T into the moduli space. And just mathematics says that that means you have a homomorphism of pi1 of T into pi1 of the moduli space. So that means you have a homomorphism from the magnetic weight lattice into Z, and that's the homomorphism I was calling mu. Well, it's fine to give it a name, but what is this mu? That had us stuck for a long time. But using the relation of the moduli space of monopoles to the space of rational maps from CP1 into something called the flag variety, we prove that mu of lambda has a very simple formula. It's just the inner product of the magnetic charge with lambda in the killing metric in the normalization where the length squared of the long root is 2. Okay, so these isometries are these powers of this of the generator, and they only generate a subgroup of the deck group where R is, roughly speaking, the GCD of the magnetic charges. It's exactly that in the simply laced case. So we've got to put an extra restriction on the kernel here, and that's what I think the semiclassical smooth vanilla BPS space looks like. Okay, so that's the end of that. Now let's apply it. So we would like now to combine the above picture with those results on n equals 2, d equals 4 super Yang-Mills. The no exotics theorem, the wall crossing, and possibly there'll be time for exact results on line defect vevs. Let's begin with no exotics and the generalized Sen conjecture. So item 1 is, what are exotics? What are exotic BPS states or exotic framed BPS states? Okay, so let's define that. So we have these spaces of BPS states, and we're talking about particles here. When you talk about particles, you're talking about a unitary representation of the super Poincare group, and so you have to represent the little supergroup. And it has, in the little supergroup, there's an SO3 for rotations around this massive particle, and then there's a global SU2R symmetry rotating the supercharges. Okay, so these spaces are going to be representations of SO3 plus SU2R. Now, in the case of vanilla BPS states, these spaces always have the form of a half hypermultiplet times an internal space. And in this semiclassical picture, the half hypermultiplet is easy to understand. That comes from the kernel of the Dirac operator on R4, the center of mass degree of freedom. In the framed case, there's no translation mode, so there's no half hypermultiplet factor, so let's just call H bar the internal space. Definition. Exotic BPS states are states in H of gamma transforming non-trivially under SU2 R-symmetry. Okay? The no exotics conjecture / theorem is that they don't exist. That SU2R always acts trivially on H of gamma. And the theorem is, basically, it's true. So, in a paper with Emanuel Diaconescu and a number of other authors, we showed this for pure SUN vector multiplet theory for the vanilla states and also for the framed states in the case of a purative line defect. And Sen and Delzato extended that to a simply laced G. Now, the way we did it is we used some very fancy mathematics about the motivic structure of the representation of the moduli space of representations of some quiver variety. And recently, Clay Cordova and Thomas Dumitrescu have given the right proof. The right proof is it's just Ward identities, stupid. It's just supersymmetric Ward identities. It's a version of, they like to say it's a version of the Weinberg-Witten theorem, which, if you remember, uses some simple Ward identities, some current algebra ideas. And their statement is that any theory with a Sonius energy momentum supermultiplet satisfies the no exotics conjecture, and that's certainly the case in the theories we're looking at. And as far as, I bug them all periodically, have you done the framed case yet? And they always say no, but it will be easy. So far they've done the vanilla case. Anyway, it's true, so let's apply it. Okay, so what is the mathematical interpretation of this no exotics conjecture? Well, we need to understand the geometry of this R-symmetry. So we have a moduli space. This could be M or M bar. Suppose its real dimension is 4n, so that means that the Riemannian holonomy is SO4n. But of course, it's hyperkähler, so the true holonomy group is in the unitary symplectic group. And SU2R, by definition here, is the commutant of the unitary symplectic group. So it acts on the tangent bundle, rotates the three complex structures. And back in the collective coordinate quantum mechanics, there's a very explicit formula for the generators of that SU2R symmetry. The omega R here are the three Kähler forms. The chi mu's become gamma matrices, so this automatically has a lift to the spin bundle. And these generators actually don't commute with the Dirac operator, but they do preserve the kernel. Okay, so the SU2R is acting on the geometrical BPS space this way. Very similarly, there's an SO3 action on these moduli spaces, and suitably defined, it commutes with the SU2R. And again, it doesn't commute with the Dirac operator, but it does preserve the kernel. So we have the following situation. We have these isomorphisms of physical and mathematical spaces. They're both sides are representations of SO3 plus SU2R, and these are meant to be isomorphisms as SO3 plus SU2R representations. Okay, so now we know from no exotics that SU2R is acting trivially here. So what does that mean over here? Well, you see, when you lift the SU2R to the spin bundle, then SU2R times USP2 maps into spin 4n, and that mapping is such that the element -1 in this group here goes over to what's called the Clifford volume form in math, or the chirality operator in physics. You might ask me how that's oriented. It's oriented by the natural complex structure orientation on the moduli space. And this has to act as 1, so this has to act as 1, so that means all the spinors in the kernel have chirality +1, which means that the index of the Dirac operator is the absolute number of BPS states. Okay, so the absolute number of BPS states is the same as the index. Oh boy. So that is a revelation. That's really nice because, this kind of question arises frequently in BPS theory, and it's always a vexing question. Okay, you calculated the index, but what do we actually know about the BPS space? Here, it's on the nose. Okay, we can go further. You could choose any complex structure on M, and then This spinor bundle can be thought of as, spinors can be thought of as 0p forms. And a combination of supersymmetries is just the D-bar operator plus the 0, 1 part of this G vector wedging. And the SU2R becomes Lefschetz SL2. So here are the three generators of Lefschetz SL2. Let's focus on the third guy here. It acts on 0q forms by measuring the degree q. So the real dimension of the moduli space is 4n. The complex dimension of the moduli space is 2n. So n is the middle dimension in the complex sense. Okay? So this has to act trivially because SU2R acts trivially. So this has to vanish. So what this means is that the L2 cohomology, the L2 0q cohomology of this D-bar operator, or more properly the D-bar operator perturbed by this, where y is any element of the Lie algebra, it vanishes except in the middle degree and is primitive with respect to Lefschetz SL2. And now to answer Nadi's question, you can add matter to the story, and we're in the midst of doing that. Of course, again, this is something that goes back to Manton and Schroers, and again, people in the audience were writing about this in the mid-90s. You add matter hypermultiplets in a quaternionic representation of G, and what that does is that gives you a bundle of hypermultiplet fermion zero modes over M, and E is associated to what's called the universal bundle, and you can show the universal connection is in fact something called a hyperholomorphic connection. Now, nobody seems to have gone and calculated the rank of E in the general case, so I did that with a student. And this is the formula. You have a sum over the weights. It depends on the Higgs vev in that way I indicated at the beginning of the talk. It has a term coming from the complex mass. And if we choose a complex structure on E, then states are now L2 sections of the spinor bundle tensor, this. And that's over relative or framed moduli space. And so we have a generalization. So the L2 cohomology of the D-bar operator with values in this bundle here. And now as you see, if you specialize to SU2 n equals 2 star, that's the vector multiplet theory where you add one hypermultiplet in the adjoint. And of course, if m goes to 0, that's n equals 4 super Yang-Mills. And then this statement reduces to the famous Sen conjecture, right? Because then the states are differential forms. And we're saying that the only harmonic forms are concentrated in the middle degree. That's the Sen conjecture. And so this is what I call the generalized Sen conjecture. And it follows from the no exotics theorem. Okay, so second application, let's talk a little bit about wall crossing. So again, let me give you the overview and then go into a few details. Now here's an easy fact. There are no L2 harmonic spinors for the ordinary Dirac operator on non-compact hyperkähler manifold. And that means that if we take that Dirac operator and we put the Higgs vev y, curly y infinity to 0, then there are no states unless the relative moduli space is just a point. Otherwise, it's non-compact and there are no states. So that means that in that chamber, the spectrum is just like it looks in Seiberg-Witten theory for SU2, with one Dion tower for each simple root. Now, other semi-classical chambers, for a variety of reasons, are known to have non-simple magnetic charges filled, and so there is non-trivial semi-classical wall crossing. Again, the theme of this talk is that higher rank is different. And that leads to some interesting math predictions. So the L2 kernel of the Dirac operator jumps, and as I just explained, the harmonic spinors have definite chirality, so the L2 index jumps. Now, how can an index jump? The whole point of the index of an operator is that it doesn't jump as you change parameters, the parameters being, say, the Higgs vevs, y and x. Well, how can that happen? Of course, what happens is that along, as it turns out, hyperplanes, and just say the space of y's, the Dirac operator fails to be Fredholm. The continuum comes down and mixes with the zero modes. A similar picture was proposed in a special case by Mark Stern and Pilgin-Yi. What we've added is we've given explicit formulae for these jumping loci, and because of the nice progress in n equals 2 theory, we can say exactly how the BPS space jumps. So in the vanilla case, we have the formula of Kontsevich and Soibelman. And in the framed case, I worked out a formula with Davide Gaiato and Andy Knightsky. And actually, the framed wall-crossing formula is easier than the Kontsevich-Soibelman wall-crossing formula and implies the Kontsevich-Soibelman formula. So I'll tell you a little bit about the framed wall-crossing formula. So what exactly is jumping? Well, it's the BPS indices, or rather the BPS protected spin characters. So on these framed BPS states, you just take the character with respect to the SO3 rotations. And so that's some Laurent series in Y, a Laurent polynomial in Y. And for a given line defect, you sum over all the electromagnetic charges with some bookkeeping device V sub gamma. Okay, so that gives you a generating function of these indices. Now, where does it jump exactly? It jumps across walls, which are given by this linear equation in Y and X, and depends on a charge, gamma H. So those are the walls W of gamma H. What's gamma H? Gamma H is any charge that supports a vanilla unframed ordinary BPS state. So if you have a vanilla unframed ordinary BPS state, it produces a wall, and across that wall, the framed states jump. Okay, now how do they jump across these walls? Well, interestingly, to describe how they jump, you should promote these bookkeeping devices to a Heisenberg algebra, and then, so now it's non-commutative, and then f of L jumps by conjugation with an operator S, where S is a certain extremely well-known operator-valued function of V of gamma H. I'm not writing out S because I don't want to overload you with formulas, but it's known. So let's look quickly at some examples. So let's first look at semiclassical vanilla wall crossing. So that didn't happen in SU2. So that's not in Zyberg and Witten's paper. They analyzed the spectrum, and there's no wall crossing out in the weak coupling regime. But it does happen as soon as you get to SU3, and in fact, that's already in a paper of Gauntlet et al. From 2000. Question? Not. Yeah. That's right. That it does. Sorry, Nadi. Yes, that's right. It does, of course, with matter. So with SU3, let's look at this funny magnetic charge, the sum of two simple co-roots, and I'll explain why on the next slide. And now this is gamma E is an arbitrary electric charge, and you see, if you have a state with these electromagnetic charges, then gamma is obviously naturally a sum of gamma 1 and gamma 2, where these are simple co-roots, and so the constituent BPS states exist. So there's the possibility for for a bound state to fall apart. Now, why choose the sum of simple co-roots? The reason is that in this case, the relative moduli space is extremely simple. It's the Taub-Nut space. And we know a lot about the Taub-Nut space. And not only that, the zero modes of exactly the Dirac operator we need were worked out in 1978 by Chris Pope. Of course, he wasn't using this language. He was thinking about neutrinos and a gravitational instanton, but the mathematics is exactly the same. We redid the calculation from scratch. It's pretty non-trivial. And so you can use that old calculation, or you can just do it yourself. Now, what do those zero modes look like? Well, here's a picture of Taub-Nut. So Taub-Nut is a circle fibration over R3, and so there's a radial direction on R3, and there's a Hooft fiber direction d by d psi. So the killing vector field g of y is proportional to derivative along the Hooft fiber with a coefficient that's a function of the Higgs vev. And you can show that states of definite electric charge also have definite parallel transport in the psi direction, given by the difference of the electric charges, that's this mu. And then the zero mode looks like this. I'm suppressing the angular dependence. And so here's a picture of Taub-Nut again. And so that has a profile as a function of the radius. That's the radius on the relative monopole moduli space. It looks like this. Its maximum value is at mu over c minus mu. And you plug that back in and write it in terms of gauge theory variables. And you find it's exactly the formula that Frederick Deneff wrote for the bound state radius a long time ago. And so the picture of the wall crossing is what we've always suspected, that C is a function of y, and as y approaches the wall, C approaches mu. This sort of broadens out, and the tip moves out to infinity. Okay, and that's how your states are disappearing from the Hilbert space in great detail. Now, what about semiclassical framed wall crossing? That already happens for pure SU2 theory. So now the Cartan is the real line. Remember, the framed wall crossing, the walls of the framed wall crossing are determined by the ordinary vanilla BPS states. And Zyberg and Witten told us what the ordinary vanilla BPS states are. And so for our purposes, they only have magnetic charge 1 and arbitrary electric charge. This is the formula for the wall. A wall in a one-dimensional line is a point. And so we get these chambers, Cn. Okay? So let's take a line defect to be a pure 't Hooft defect of charge p over 2. And we form our generating function, and we form our Heisenberg algebra with two generators, V1 and V2. So the general V sub gamma has electric charge Ne and Nm, and we can normal order it. If we normal order it, we get some power of y. And here's the formula. You can get this by wall crossing. You can get this by fancier techniques. There are all sorts of ways of getting this formula. Now, this is a complicated formula. What is this? So UL, that's a Chebyshev polynomial. And the Chebyshev polynomial is evaluated on FL. L is the chamber we're looking at, C sub L. And FL is this mess. Okay, so what you're supposed to take away from this is there is a compact formula. It is non-trivial. And if you expand it out and normal order it, you get an infinite number of predictions for the kernel of the Dirac operator as a spin representation for monopole moduli spaces of arbitrarily high magnetic charge or arbitrarily high dimension. So that, I think, will be a challenge for the mathematicians to reproduce. So real quick, let me just indicate a few future directions for this line of research. So you can add matter and arbitrary 't Hooft Wilson lines, working that out with a student. It would be nice to understand even better how the Fredholm property of the Dirac operator fails in the general case by using the asymptotic form of the monopole metric. And it's very interesting to combine with the localization result of Ito, Kuda, and Taki, combine that with the Darboux expansion that I had with Gaiato and Knightsky. And the goal here is to produce a kind of L2 index theorem on non-compact monopole moduli spaces where no off-the-shelf theorem exists. So really quick, I'll say something about projects 2 and 3. So how to understand better about the Fredholm property failing? Well, there's a known asymptotic formula for the metric on moduli space when there are widely separated monopoles whose charges are simple roots. And so you look at this kind of limit, where you take two clusters, and each monopole with simple roots is very far separated. It's like a star, so it's very far separated on the length scale of the theory, and then the clusters are hierarchically even further apart. And in that case, the relative moduli space splits into two components and a four-dimensional space, which we think is Taub-Nut. So probably the Taub-Nut example is actually giving the universal picture for how wall crossing works, how the Fredholm property fails. So stay tuned. That's work in progress. Now, for the line defects, well, there are methods to calculate the VEVs of supersymmetric line defects on R3 times S1 exactly. So there's a kind of expansion I gave with Gaiato and Knightsky in terms of some functions which are explicitly computable. So my favorite example here is the supersymmetric Wilson line in SU2 gauge theory, the trace and the 2. And it's a three-term expansion where these are explicitly known functions. They give you the weak coupling expression plus known non-perturbative series. And this is a surprising non-perturbative correction having to do with a bound state of a monopole with a Wilson line. On the other hand, there's been a lot of activity in localization theory. And in particular, Ito, Okuda, and Taki gave expressions that have this shape, for those who know. A and B are complexified Fenchel-Nielsen coordinates, and the z's here involve integrals of characteristic classes over moduli spaces of singular monopoles. So it turns out to be very tricky to try and compare these two formulas. The change of variables is very subtle, but the hope is that that will produce a kind of L2 index theorem on these non-compact spaces where no theorem exists. So I'm out of time. I realize that's too much information. So if you go back to your home institution and somebody says, oh, what did he say? You could just remember recent, new, old. Recent results on n equals 2 four-dimensional super Yang-Mills imply new results about the differential geometry of old monopole moduli spaces. Thanks for your attention.
Can I ask? What happens to the original, maybe a simple-minded question, Dirac quantization condition, which led to the prediction of existence of monopole, led to the electron
the Dirac
mass
quantization.
in this generalized
Yeah, the Dirac quantization condition.
Excuse me. Does this general formulation somehow say that a monopole, single monopole, cannot exist? There's something more different connections.
I don't understand the question.
Dirac quantization condition led to the prediction that existence of a single monopole related to the electron mass. Right? That was the beauty, and that led to Hooft-Polyakov monopoles and so on. I'm talking purely electromagnetic monopoles. So this generalization, does it lead to any contradiction of the Dirac quantization condition?
Certainly not. I'm probably not understanding the question. So the Dirac quantization condition is the statement that gamma m is in the co-root lattice. Jeff?
You defined singular monopoles in terms of solutions to the Boltzmann equations with certain asymptotics. And for the D-Brane picture, it would seem that using NOM's equations or modification of NOM's equations would be a very natural thing to
Absolutely.
do.
Yeah.
Is that helpful in this, useful, shedding light on what's going on?
It's one of those things I'd like to do, and we keep telling ourselves that we ought to look at the NOM equations on a semi-infinite interval. Maybe Anton's done this. I mean, it's a very natural thing to try and do, and so far it hasn't been particularly insightful for us, but it's definitely an interesting thing to look into.
Hi. I have a question about you mentioned about you are trying to comparing the localization result of Okuda and your GMM prediction.
Yeah.
There are one thing that I was considering about when we are adding the hypermultiplate into our system. I remember that Nysky had a paper saying that we can build a higher rank of higher charged two-hoof line by using the minimum building blocks. And it turns out when there are hypermultiplates, the result of localization and this building block method does not match. So do you have any ideas about this situation?
Okay, I don't know. That sounds extremely interesting, but I don't know what you're talking about. So please tell me about that afterwards. That sounds very interesting.
Right. Excuse me, I have two questions.
Yeah.
The first one is just to make sure I understood the no exotic statement.
Mm-hmm.
Can you phrase that strictly as a statement about a quantum mechanical quiver theory that you could write down for each set of
Yes,
charges?
absolutely. Yeah.
And that quantum mechanical quiver theory would have some action of SU2R. And there you expect the index to not be an index, but actually count.
Okay, so the question is, I don't think Sav's mic was working. The question is, what does the no exotics theorem imply about the moduli space of representations of a quiver? And the answer is, that's in this original paper with Diaconescu and Manscott and Chuang and Jan Soibelman, and I hope I haven't left somebody off. The answer is kind of interesting. No exotics implies that the Hodge numbers are purely diagonal. In other words, HPQ is 0 unless P equals Q.
So one more quick question. So from the new results you've obtained, can you learn something about the formal integrals that would correspond to Euler characteristics? Or
Good heavens. So in the beginning of the talk, I alluded to papers in the mid-90s where Sav and Jeff made predictions, and Sav indeed made some interesting predictions for the integral of the Euler characteristic over these moduli spaces by looking at higher derivative corrections to super Young-Mills. And it's too early to tell, but what we're certainly getting are equivariant characteristic classes, and they do involve the Euler class. Okay, in this comparison with the localization of the so-called Darboux expansion with the localization result. On the localization side, you're definitely getting integrals of characteristic classes, including equivariant characteristic classes that include the Euler characteristic. Now, whether one can, turn the knobs and push the buttons so that you only get the Euler characteristic, I don't know. But the possibility definitely exists.